Before we move on to the planning algorithms, I want to tell you a little bit more about heuristics and specifically what makes a good heuristic and how do we find these. We have defined a heuristic in a technical sense as a function that estimates the distance to the nearest goal node. But a heuristic obviously has a colloquial meaning as well, and that's what's defined here. So heuristics are criteria, methods, or principles for deciding which among several alternative courses of action promises to be the most effective. So the alternatives that we're looking at are, of course, the successor nodes that we want to evaluate. We want to see which one of those is the most promising. And what we need to do is we need to decide which one to follow first. Of course, we keep in mind the others and follow those later. We use heuristics in everyday life. For example, here you see a heuristic for deciding whether a pineapple is ripe. If you ever go into a shop and want to buy a ripe pineapple, this may work for you or it may not. So if you can rip out the inner leaves easily and the fruit smells like a pineapple should smell, then you're looking at a ripe pineapple and this is one you can buy, assuming the price is right. If there are no pineapples where you are, tough luck. The reason why I've circled the word deciding here is because this gives us a different idea of what a heuristic can be. All we need from a heuristic is just a decision which alternative looks best. So it doesn't really need to be related to the distance to the goal at all. All we need is a function that decides which one is the best node. If we had that function, that would constitute a perfect heuristic, because it would tell us which successor to follow and which path we should explore first. If that deciding is correct, then we have a perfect heuristic. Another example of a heuristic you've applied probably not too long ago is in choosing this course. You looked at the introductory material to this course and used this as information to decide which of the courses that were available you want to take. So you used heuristic information about the course to make this choice. Okay, assuming you understand what a heuristic is, now the question is, when is a heuristic a good heuristic? And if we have a given search problem and a given heuristic, we can evaluate that heuristic by looking at the number of states that are generated for a specific problem with that heuristic. And if we had two heuristics, we could compare them by using the number of states they generate to see which is better. The better heuristic would generate fewer states. But that is only a heuristic for deciding which heuristic is better. Because what we are really after is we want solutions as fast as possible, so we have time constraints to respect. And computing a good heuristic also takes time. Unfortunately, this means we're dealing with a trade-off here. And this is the trade-off. Some heuristics are simple, so they provide a simple way of discriminating between the successors we generate. And since we want to optimize the time we take during search, simplicity here means easy to compute. We want to have a fast way to compute the heuristic value for a given state. But heuristics that are simple to compute are often not accurate, and accurate is the other property in our trade-off here. A heuristic, unless it is perfect, does not provide a guarantee that it tells us which the best successor is to explore next. So there's no guarantee that it identifies the best course of action. But if it's a good heuristic, it will do this more often than a heuristic that is not as good. So a good heuristic does this sufficiently often. It's accurate. It tells us which is the best course of action, or in the technical sense, it tells us how far the goal state really is. So now we know what a good heuristic is. The important question then is, how can we find good heuristics for a given problem? This is somewhat similar to the problem of problem formulation. It's a meta-level problem. We have to find a good heuristic to do good search, just as a good problem formulation will ease search. That means this is a very important question. And the answer is, there are methods for doing this, and we will look at some general methods next. But then there is a different question that is just as important. If we have a method, can we automate this method? And the answer again is yes, but that's a very complex process, and we will get to that later in this course. In fact, automatically finding good heuristics has probably been one of the most hot topics in AI planning research over the last 10-15 years. So here's a general method for finding good heuristics, and the idea is based on a simplified problem or a relaxed problem. Usually a problem is defined in terms of states and actions that are applicable in states and achieve certain things in successor states. So what we have is restrictions on these actions, when they are applicable, when we can use them, and in which states they are useful. What we can do is relax those restrictions. So we can look at the restrictions defined in the original problem and drop some of them or make them less hard. And that gives us a new problem, which is the relaxed problem. And then the following should be fairly obvious to see, namely that the cost of an optimal solution for a relaxed problem is an admissible heuristic for the original problem. In fact, it's admissible and consistent, but since we haven't defined consistent here, I won't go into that. So you should see why it is admissible. It's very simple to see. Because the optimal solution for our original problem is, of course, also a solution for our relaxed problem. We've only relaxed the restrictions on the actions. So an optimal solution for the relaxed problem can have at most as many steps as the optimal solution for our original problem, because that is a solution for the relaxed problem. In general, what we have is that in our relaxed problem, we allow shortcuts to be taken with these relaxed actions that are not possible in our original problem. So if we take out these shortcuts, we end up with longer solutions. And since this method is quite abstract, I want to illustrate this with an example, and we will use the 8 puzzle that we've seen before and the actions that are defined for this 8 puzzle. So here is the original condition that we had for the applicability of actions. Namely, a tile can move from square A to square B if A is horizontally or vertically adjacent to B and B is blank. So the condition we have here is a conjunction of two subconditions, and that should tell us how we can build a relaxed condition quite easily, namely by dropping one of the two parts or both of them. And this is how this works. If we drop the second part, that B is blank, we end up with this heuristic here. And that tells us a tile can move from square A to B if A is adjacent to B. I've dropped the horizontally or vertically. And what we get there, of course, then is the Manhattan block distance heuristic, because we now allow a tile to be moved no matter where it is moving to, which gives us exactly the block distance for this tile. And if we add all those up, that's the Manhattan block distance we've seen. The second one is if we drop the first part of this definition, so that the adjacency condition is dropped, then we end up with a heuristic that the tile can move from A to B if B is blank. And finally, we can have a heuristic if we drop both conditions that says a tile can move from A to B and there are no conditions. And of course this then gives us the misplaced tile heuristic. We simply count those tiles that can move to where they need to be in one step, because there's no conditions on how they can move. So what you see here is we've derived two of the heuristics that we've already used for the 8 puzzle using the method we've just introduced by using relaxed conditions of the actions that are applicable in our problem. So this concludes this section of the course on AI search technology and the A-star algorithm. You should understand now that a heuristic function encodes problem-specific knowledge in a problem-independent way by mapping a state to a real number. This information about search states can be used to make the search more efficient. In general, this is done by using an evaluation function that tells us how good a search node is. Greedy best first search simply uses the heuristic function as the evaluation function, but a better solution is provided by the A-star algorithm. The evaluation function used by A-star is simply the sum of the heuristic function for a node plus the cost of getting to that node in the first place. We have also seen that A-star is optimal. It will always find an optimal solution, and it is optimally efficient. It does not expand more nodes than absolutely necessary. But I've also shown you that A-star is not the answer to all questions, specifically when it comes to graph search. Finally, since good heuristics are so important for A star, I've also talked a little bit about what good heuristics are and how to find them. So now a big tick because you understand all of that.